In the previous lecture, I gave you a quick introduction to the course and described the contents of the course and what is expected in terms of the learning outcomes of this course. And also, I discussed about the assessment policy in the previous lecture. Now, in today's lecture, we're going to dive into the topic and get started with the signals. Okay, this course is signals and systems. So today I'm going to focus mostly on signals, and later on we will be covering systems as well. Now, if you recall from the previous lecture when I gave the introduction, signals arise in a variety of contexts. Okay, it's not just for electrical engineering. Signals arise in all sorts of domains, which could in all aspects of engineering as well as in finance and a host of different contexts. So signals are basically functions of variable with respect to one or more other independent variables, and systems are those things which would process those signals to convert them into a form that we desire them to be in, or to perform some operations on those signals. So this course deals with the signals itself, and we'll also discuss about systems later on, where we'll see how we design certain systems to process those signals. So as I said, the definition of a signal is that it can be a function of one or more independent variables. Generally, the independent variable can be any variable, but in the context of this course, we would have time as our independent variable. And rather than having multiple independent variables, we will be focusing our attention in this course to a single independent variable, which is going to be time. So, for example, we can have a signal which is a function of time. So the independent variable t, which is time, is on the x-axis, and the signal that is varying as a function of time will be on the y-axis, which we can denote as x of t. So for example, if we have a signal like this, that could represent as say the wind speed or the voltage across a capacitor changing with time. So in an electric circuit, for example, if we have a battery connected to an RC circuit, so let's say we have a resistor and capacitor in series, and there is a voltage across this capacitor, we can have this voltage changing with time plotted on a graph as a function of time. So that x of t would be the voltage across that capacitor, which is changing with time. So that's an example of a signal. So this particular signal is a function of time. Or we can have our, say, speech signal changing with time. So as we speak, the speech signal could look something like this, right? So that's a function of time. So we'll call that as another x of t. So the speech signal that is produced is basically the variations of air pressure caused by the sounds that we produce, which is changing with time. So we can have that as another example of a signal. Again, here the independent variable is time, which is on the x-axis. Okay, and we could also have other examples of signals. For example, so let's say we have height as the independent variable and the wind speed as the dependent variable. So how does the wind speed change with altitude? As we go higher and higher and higher, what happens to the wind speed? So if we have to plot the wind speed as a function of time, what does it look like? So does it increase with altitude or decrease with altitude? So typically the wind speed looks something like this. So with altitude, as the height increases, the wind speed also increases, and at a certain point it becomes kind of flattened out. So Now here we have given an example of a signal which is a function of an independent variable which is not time. Okay, here the independent variable is the altitude above the ground, the height above the ground. So we have seen here an example of a signal which is a function of the altitude. But generally in this course, as far as this course is concerned, we will be having a signal which is a function of time. So more often than not, the x-axis will be the time variable t, and the y-axis will be some function of t, which we'll call as x of t or y of t or v of t, whatever name notation we give it, but it will be a function of time, and the signal can look in any particular form. Now, if you notice all these signals that I have shown as examples so far, they are all continuous functions of time. So if you notice, these signals are defined for all values of time. It is continuous. This is also continuous. And this is also continuous function of height. This is a continuous function of time. So all these signals are continuous functions. So that brings us to our first category of signals, which is called as continuous signals. Continuous signals are, as the name suggests, continuous functions of time. That means the signal is defined for all values of time. So we can have the value of the signal for t equal to, say, 0, 1, 2, 3, and so on. So the signal is defined not just for integer values of time, but also for 0.1, 0.2, 0.22, 0.234, and so on, right? So it is defined for all values of time. And the general notation that we will use throughout this course to represent a continuous signal is as some function of time. So we'll have these parentheses. So that's the general notation. Any variable, we can call this as x or y or v, but it will be a function of time within round brackets or parentheses. Okay, so the general notation for a continuous signal is as such. And we will be using this notation throughout this course. Okay, so a continuous time signal will be denoted as whatever the name of the signal is, x, y, h, v, whatever, but it is a function of time, so we'll put time in parentheses or round brackets. Okay, so continuous time signals, also called as continuous time signals, okay, because they are functions of time, so we will sometimes also refer to them as continuous time signals. Okay, so that's the first category of signals that we are going to discuss. Now, just as we have continuous signals, the opposite or the other variation of the continuous signals, the other type of signals that we will cover in this course is called as discrete time signals or discrete signals. So let's give some examples of discrete signals, and then we'll go into more specific details. Now, if we look at this particular example of a signal, we notice that this is not a continuous function, but rather this function is described at discrete instances or discrete indexes of time. So, for example, this function has a value at this instant of time, and it has a value at this second instant, and so on. So such kind of signals are called as discrete signals. Discrete signals, or to be more specific, discrete time sequences. And what we notice here is that the independent variable will be an integer number, which is n. So n should always be integer, and that means this function is defined only for integer values of n. So that means if that is 0, we can have it at 1, 2, 3, 4, 5, 6, 7, and so on. And similarly, we can have it at a value at 0 as well, or at -1 as well. Say -1, -2, and so on. So we can have it at -1, -2, but the value of n should always be an integer. So discrete signals are denoted as some variable, whatever is the name of the function, as a function of the index n, and we always represent the discrete signal by putting that independent variable n inside the square brackets. So the general notation for a discrete sequence is x of n, general notation, okay? And the condition is that the value of n should always be integers. N takes only integer values. Okay, so a typical example for such a discrete sequence could be the stock market index for different weeks in the year. So in week 1, what is the value of the stock market and the index of the stock market in week 2, and so on. And when we talk about negative values, it can mean what it was presently today, or this week, or the previous week, and 2 weeks before, or 1 week ahead, 2 weeks ahead, and so on. So we can have the reference given to this n depending on the context, but the important point here is that n, the independent variable in this case, takes on only integer values. So the function here is defined only for integer values of n. So we denote this as x of n within square brackets. So the independent variable n, so in a discrete sequence, the independent variable is denoted as n in square brackets. Okay, and just to summarize, discrete, we have two types of signals. Okay, the first is the continuous time signal, the second is the discrete time signal. Now the discrete time signal itself can arise naturally from the source from which we are getting the signal, like the example of a stock market, where we measure the stock market index on a weekly basis. So in week 1, what is the stock market index? In week 2, what is the stock market index? So it is available, that information is available on a weekly basis. In between the week, there is no information available. So the signal is inherently defined at those discrete instance. But sometimes a discrete signal can be obtained from a continuous signal by sampling the continuous signal at specific instance or specific moments of time. So a discrete signal can occur naturally, or sometimes we convert a continuous signal to a discrete signal because that facilitates a lot of processing in a simpler way. So what that means is that we can have a continuous signal. So what we have here is a continuous function of time. But if we sample this continuous signal at specific instance, say we sample at this instant, at this instant, at this instant, and so on. So at these instants of time, we are going to sample the signal and find out what is the value of the signal at that instant of time. So it has this value. So the next value is here, and the next value is here, and the next value is here, and so on. So in this case, we have obtained the discrete signal from the continuous signal. So this value will be 0, 1, 2, 3, 4, 5, 6, 7, and so on. And we can have -1, -2, and so on. So this curve here is continuous, denoted as x of t, and these lines here with the dots, they are the samples of that signal, of the continuous signal x of t. So all these are denoting the samples x of n. So the sample at index 0 is having this value, at index -1 is having this value, and so on. So we can have the samples or the discrete sequence obtained by what we call as sampling the continuous signal. Again, what is sampling? We will cover this towards the latter part of this course, and you will also come across sampling in future course in your higher level in advanced communication systems. Okay, so when you study digital communication, you'll come across the concept of sampling, but we will just give a brief introduction to sampling later on in the latter part of this course. But what I want you to understand here is that when it comes to discrete signals, the discrete signal can occur naturally from its measurements itself, or we can have a continuous signal which we can sample and convert it to a discrete signal. The reason why we would do that is because with a lot of processors in the present day, it becomes much more convenient and more powerful to deal with the signal and process the signal when it is in the discrete in time rather than continuous in time. So that's why we would convert the continuous signal to a discrete signal. So now just to summarize very quickly what we have discussed so far, we have talked about signals which are of two types. Okay, the first is a continuous signal, and the other is a discrete signal. So this is a continuous function of time. So the independent variable is time, that we denote by the letter t. So the general notation is, you can write it as x of t or y of t or v of t, whatever name we can give it, but it is a function of time, and we'll put that in parentheses or round brackets. In contrast, the discrete signal has the independent variable is an index, which we denote by the letter n, and we would represent the signal or itself as x of n or y of n or v of n, and all of this in square brackets. Okay, so the distinction in the notation for the continuous and discrete signals is that for the continuous signal, we would more often than not use time as the independent variable, and that would be denoted within the rounded brackets or parentheses. And for the discrete signal, the independent variable is an index, is a number, and that would be denoted within square brackets, and n can take only integer values. Okay, now the next thing that we are going to do is I will show you some examples of common signals and important signals that are used as that are the building blocks of some of the tools that we will use in signal processing and communication. Okay, so I'll give you some examples of those signals, and later on we will also discuss the properties of those signals. So I'm going to start with some examples of fundamental types of signals which are important and will be used as foundations in a lot of signal processing and signal analysis tools that we'll study in the latter part of this course. So I'm going to give you examples of such types of signals. Now, well, when we denote the discrete sequence or the discrete signal as a function of the index n within square brackets, well, and n takes on only integer values, just to give you an idea how we interpret this, let's look back at our discrete signal. So this first sample here, which is having the index at -2, so that corresponds to x of -2. So this one will correspond to x of -1. And similarly, this third sample here, this will correspond to the value of x when the index is 0. So we will denote that as x of 0. And the next one would be x of 1, because the index here is 1. And the next sample would be x of 2, and so on. So that is how we represent and denote each of the samples. So as you can see that these index values can take on only integer numbers, okay, integer values. They cannot be fractional numbers. So these indices for the discrete sequence should always be integers. So the n value that the discrete sequence or the independent variable n can take only integer values in the case of discrete signals. So I'm now going to introduce you to the first type of continuous signal, which is important in the study of this course and which will be used a lot in the tools that we are going to use for the analysis of signals. It's a kind of a building block for many of the signals or more complex signals that we will study later. Okay, so I'm going to introduce the first type of signal, and we will be seeing both in the continuous time domain as well as in the discrete time domain. So what we have here is a sinusoidal signal which is continuous in time. So this is an example of a continuous time signal where we have time as the independent variable on the x-axis and the amplitude as a function of time on the y-axis. Okay, again, just for the theoretical purposes, I've showed the time and the negative side as well. So we can have the time extending from -infinity to +infinity. Okay, so it is a continuous function of time, and this is the first category of important signals called as the sinusoidal signal. And because there's another kind of sinusoidal signal which is complex in nature, that means it is a complex signal having a real part and an imaginary part. This particular one is the real sinusoidal signal, and it is continuous in time. So we denote it as x of t, as has been shown here. It has an amplitude of 5 volts. So that means you notice here on the y-axis, the peak amplitude is 5, and on the negative side it's -5. So we have here 5, so that's exactly halfway between 4 and 6. So that's the peak value, and on the negative side it has a peak value of -5 volts. So this 5 that we have here denotes the peak amplitude of the sinusoidal signal. and this omega naught corresponds to the frequency of the sinusoidal signal. Okay, so in general we write it as a cosine omega naught t plus phi. So the sinusoidal waveform is described using three parameters. A is the amplitude, and this omega naught, so we have this A, and the second parameter is omega naught, and the third parameter is the phi parameter. So omega naught is the angular frequency, and the unit for omega naught is radians per second, and omega naught is defined as 2 pi f naught, where f naught or f0 is the frequency in hertz, or we call it as cycles per second. So see, cycles per second. Now what that means is how many cycles of this waveform occurs in 1 second. So if you notice here, from 0 to 1 it is 1 cycle. After that the same thing will repeat. So it starts at the peak, goes to the bottom peak, and comes back to the top peak. So that is 1 cycle. So after this the same thing is repeating. So that corresponds to 1 cycle, and because 1 cycle is taking 1 second of time interval, so that means there is the frequency of this waveform is 1 cycle per second. So that corresponds to a frequency of 1 hertz in this particular example. Right, we'll come to that later, but what I want you to familiarize now is to get acquainted with the parameters that are used in representing the signals using a mathematical representation. So the first parameter is amplitude, the second parameter is angular frequency omega naught, which you can write in terms of cycles per second as 2 pi f naught. So you can write this as a cosine 2 pi f naught t plus phi. Okay, and now the third parameter phi is called the phase shift. Okay, now in this particular example I have used a cosine wave with a phase shift of 0. So this particular example has phi equal to 0. So I've used it with 0 phase shift. Phase shift corresponds to shifting this waveform to the left or to the right. Okay, so rather than having the 0 axis exactly at the peak here, because cosine 0 is 1, and 5 times or a times cosine 0 becomes a times 1, which is a, right, which is 5 in this case. So if we shift this waveform, the only thing that is going to happen is this 0 time axis is going to be shifted to the left or right, or the waveform will be shifted to the left or the right, so that the 0 time axis will coincide with some other point rather than this peak. Okay, we'll come to those things later. So now we have these three parameters which are used to represent a real sinusoidal signal, which is the amplitude A, the frequency omega naught, and the phase phi. Okay, so we have these three parameters. And as I mentioned earlier, that this waveform is continuous in time, so it is a continuous time signal. Which we denote as x of t equals 5 cosine omega naught t plus phi. In the phase phi in this case is equal to 0. Now let us have a look at the discrete version of the sinusoidal signal and see how we can represent that mathematically as well. So the discrete version of the sinusoidal signal is shown here in this figure. So this is a discrete time sinusoidal sequence. Okay, and in the discrete version, normally we call it as a discrete sequence rather than a discrete signal, because it comes out as a sequence of numbers. So we generally tend to use the word sequence in the discrete case. So if you notice here, for the discrete case, the index here, the independent variable, is n, and n takes on only integer values. So we have -10, -9, -8, -7, and so on. So each of these samples corresponds to x of -10 for the first one, because it is a sample when the n index, when the value of n is -10. Similarly, this is x of -9, and here we have x of -8, and that would be x of -7. That corresponds to x of -6. And be careful, the notation that we are going to use is square brackets for the discrete case. So that's x of -7 in square brackets. So that's x of -6 in square brackets, and that's x of -5, and that would be x of -4, x of -3, that's x of -2, x of -1, and that is x of 0, and that corresponds to x of +1, x of 2, that is x of 3, x of 4, and so on. Okay, now the general form of representing the discrete signal is x of n equals the amplitude a with the peak value a, which we have here. It happens to be exactly 5 again. So x of a, and again it's cosine, and the frequency value here, the frequency value is represented with a capital omega, just to distinguish between the continuous frequency and the discrete frequency. So we'll denote that as a cosine omega naught n plus the phase. Again, in this case, I have used the phase as 0. The phase shift here is 0. So we'll talk about the phase shift later. Okay, so now here, that is the omega 0. Okay, that's the capital omega. Omega 0 is the frequency of the discrete sequence. Okay, now so the parameters that are used to describe the discrete sequence is the amplitude a and the frequency omega naught. And if you notice here, now if we include a phase shift in this, okay, if we have a phase shift which is not 0 with phase shift, then we can denote this as x of n equals a cosine omega naught n plus some phase phi. Now what this phase shift would do, if it is not equal to 0, is basically going to shift this entire sequence to the left or to the right. Okay, I will be illustrating that in a subsequent lecture, but for now what you need to understand is that the discrete sequence is represented by an amplitude by a frequency, the discrete frequency, which is denoted as capital omega naught. And sometimes we might use the same small omega naught as in the continuous case. But the important thing is that the independent variable is going to be n, which takes on only integer values, as we see here. Okay, all these are integer values for n. Okay, so that is what distinguishes the continuous signal from a discrete signal. And the phase, as I said, if there is a phase shift, that will cause this sequence to be shifted to the left or to the right, depending on the sign and magnitude of the phase shift. So that means instead of x of 0 being this value, we can have the 0 getting shifted to here, and that would be the sequence shifted to the right by some amount. Or if the 0 axis comes here, that means the sequence has been shifted to the left by 2. So we'll be illustrating these operations with examples later. Okay, but what I want you to get clear in this lecture is how do we represent continuous time signals and discrete time signals, and what is the notation for their representation. And we have seen the first type of signals, which is the sinusoidal signal, and we have seen the continuous version of the sinusoidal signal here. And now this is the discrete version of the sinusoidal signal. As if you notice, this is basically the samples taken from a continuous time sinusoidal signal, as we will see shortly. So as I said, the black lines, the discrete sequence that we have here, are samples taken from the continuous version of the sinusoidal signal. So we have x of t phi cosine omega naught t. That's the continuous sequence shown by this red curve. And the discrete sequence obtained by sampling the continuous signal is what we have by these lines with the circle on top. So these are the samples giving us the discrete time sequence. So I've just overlaid the continuous time signal onto the discrete time sequence to show that one way of getting the discrete signal is by taking samples of the continuous time signal. So as I've said here, the discrete sequence can be obtained by sampling the continuous signal. So we get the value of the continuous signal at specific sample instance, which are integer numbers. So at when n is equal to minus 10, what is the value of the signal? When n is equal to minus 9, what is the value? And so on. So we have obtained here the discrete sequence by sampling the continuous signal. Now the next type of signals that I'm going to introduce is what is called as the exponential signals. Now here is an example of an exponential signal, and this in particular is a real exponential signal. Okay, it's real in the sense that it does not have an imaginary component. So that means there is a separate kind of signals which are complex signals, which will have real part and an imaginary part, which we'll come to later. Okay, we'll start off with the real signals first, and then later on I will also introduce you to the complex signals. Okay, so just as in the sinusoidal waveform where we had the real sinusoidal in the continuous time and in the discrete time, now we have the real exponential signal, which is continuous in time. So that's a continuous signal which is exponentially growing. Now the general form of an exponential signal is c e power at. So because it's continuous, we write as x of t. So that's the notation, and the general representation of a continuous exponential signal, continuous real exponential signal, is c e power at. Now it is a real signal when these parameters c and a are real numbers. They are not complex numbers. Okay, so when c and a are real numbers, x of t is a real signal. Okay, now the value of c corresponds to where this signal or the plot intersects with the zero time axis. So that point here, that corresponds to our c, and the value of a determines whether this exponential signal is going to be growing or decaying. So when the value of a is positive, then we will get a growing exponential signal. So this particular curve that we have here is for positive value of a, and that is why it is growing. And as you can see, the value of c is somewhere around 2. So it is 2 e power some positive value for a times t. So that corresponds to a growing exponential when a is positive. X of t is a growing exponential. Okay, now typical signal or typical observations where we can get an exponentially growing signal is from a radioactive reaction. The energy released from a radioactive reaction, like an atomic bomb explosion, what is the energy released in this thing? It keeps exponentially growing. Or the growth of a population in a certain society or certain group of animals. So these could be exponentially growing, and in that case, we have a growing exponential where the parameter a tends to be a positive value. Okay. Similarly, we can have a decaying exponential where the curve would be decreasing with time, as we have it in here. So this is also a real exponential signal that is decaying with time. So and it is decaying, and it is also continuous in time. So in this case also, the function is defined as x of t equals c e power at, but now the value of a is negative, right? So therefore the curve is decaying with time, and as before, the value of c dictates where this curve intersects with the zero time axis. So the time is 0 here, so that's the zero time axis. So the intersection of the curve with the zero time axis corresponds to the value of c, so that's our c over there. So depending on the value of c, accordingly the curve will intersect at that particular point. So this is a decaying exponential, and as before, when we have these parameters c and a to be real numbers, then this is a real signal. If c and a happen to be complex numbers, then we will get what is called as a complex exponential signal, which we will discuss later. I will introduce complex exponentials also later, because that also play complex exponentials are also an important foundation blocks of some of the analytical tools that we are going to use in this course. Okay, and if you notice, both these exponential signals, they are continuous in time. So this is continuous time, continuous in time, and so is this decaying exponential. This is also continuous in time. Now, as an exercise, I want you to think what will happen if the value of a is equal to 0. So if we make the value of a equal to 0, then what happens to both these exponential signals? So in this case, if we make a equal to 0, then it becomes c e power 0t, which is c e power 0, which is simply e power 0 is 1, so c into 1 will become c. That means when a is equal to 0, this function or the signal will just become a constant value equal to c. So whatever is c, it will be a straight line with a height of c above the x-axis, right? So similarly, in the decaying case also, when a is equal to 0, it becomes a constant, right? So when the exponent a is equal to 0, we get a signal which is simply constant. And just to emphasize, the decaying exponential signal is obtained when the exponent a is negative. Okay, now let us have a look at the corresponding exponential signals in the discrete time version. So this is an example of a real exponential sequence which is growing with the index n, and because it's discrete, the notation is x of n in square brackets, and the general form is c alpha power n. So this is a real exponential discrete sequence. Now, as in the continuous version, where we have it as c e power a t, we can define the discrete equivalent as x of n as c e power, we'll call it as beta n. Okay, now it becomes much more convenient, as we'll see later, to simply call this e power beta as some other variable. So we call we denote e power beta as some alpha. So our general form of our discrete sequence can be written as c alpha power n. So alpha is nothing but e power beta, and that way the notation becomes much simpler. So we will be following this particular notation. Now, when we have this alpha, which is equal to e power beta, to be greater than 1, then we get a growing exponential, wherein all the samples are in the positive side. If you see, all these lines are going upward. So it is a growing exponential with all the samples having positive values. Okay, and that happens when alpha is greater than 1. So growing exponential with all samples positive. Okay, and that happens when alpha is greater than 1. Okay, now we will see what happens for different values of alpha. When this is alpha is positive and greater than 1. We can also have alpha positive but between 0 and 1, or we can have alpha negative between -1 and 0, or alpha to be less than -1 as well. So we'll see all the 4 cases and see how this signal changes. Okay, so when we have alpha greater than 1, we get this growing exponential wherein all the samples are having positive values. Here we have a discrete real exponential sequence where the value of alpha is between 0 and 1. So previously it was greater than 1. It is positive and greater than 1. Now it is positive but less than 1. So it lies between 0 and 1. So this is also a real exponential sequence when alpha is between 0 and 1. And what we notice is that the sequence is a decaying exponential sequence. So you see that the values are becoming smaller and smaller as we increase the index value n. Okay, so that is a decaying sequence. And we get such a sequence when the value of alpha is between 0 and 1. Okay, you need to be familiar and get well acquainted with all these possibilities that we can have for different values or combinations of the parameters that define our signals. Okay, so again here alpha is equal to e power beta, and the general form is x of n is c e power beta n, which we can write as c alpha power n, as it has been denoted here in the plot. And what we have here is a decaying sequence, but all the sequence values are positive. So all the sample values are having the line is going upward. So for this range of alpha, that is alpha being positive between 0 and 1, then we have a decaying sequence with all positive values. Okay, next we'll see further combinations for the values of alpha when alpha gets negative and alpha becomes negative and becomes less than -1 as well. So far we have seen two cases of the real exponential discrete sequence. The first case is when alpha is greater than 1, so that is alpha is positive and greater than 1. We have a growing sequence wherein all the sample values are positive. Next we saw when alpha is between 0 and 1, then we have a decaying sequence, but all the sample values are still positive. Now we will see what happens when the alpha value is negative and it lies between -1 and 0, as well as when it becomes negative beyond -1. Okay, that is less than -1. Okay, let us first have a look at the next case where alpha is less than -1, that is it is more negative than -1. In this case again we see that it is a growing exponential. So you see that the envelope is growing, but unlike in the previous case where all the sample numbers were positive, here we see that the sample numbers are alternating between positive and negative. So positive, negative, positive, negative, positive, negative, positive, negative, and it is also growing as we increase the value of n. So they alternate between positive and negative, and also exponentially increase. So they are exponentially growing and alternating between positive and negative. So this is also a growing discrete exponential sequence. Okay, and we get this growing condition when alpha is either greater than 1 or even less than -1, or in general we say that combining these two conditions, here alpha is greater than 1, so we can write the magnitude of alpha greater than 1, and similarly here it is since it's growing but it is alpha less than -1, so we can say magnitude of the alpha greater than 1, right? So the magnitude of alpha is greater than 1. So that's another way of saying that alpha is when alpha is either greater than +1 or less than -1, we get growing exponential sequence. The only difference is that when it is greater than 1, we get all the samples to be on the positive side, but when it is less than -1, we have alternating positive and negative sample values. But in both the cases we see that they are increasing as we increase the index value n, right? And now let us see what happens when alpha is negative but it is more than -1. That means alpha lies between -1 and 0. So the final case here is when we have the discrete real exponential sequence with alpha lying between -1 and 0. In this case again we see that it's a decaying sequence as we increase the value of the independent variable n. So as we go on increasing the value of n, we see that the sample values are decreasing, but they are also alternating between positive and negative, right? So when we have alpha between 0 and 1, or between -1 and 0, so we have alpha between 0 and 1 here, it is decaying, but all the samples are positive. But when it is between -1 and 0, it is decaying, but the samples are alternating between positive and negative. So in this case, we say it's a decaying sequence. And we get this when the magnitude of alpha is less than 1. Okay, when the magnitude of alpha is greater than 1, that means when alpha is higher than 1 or lower than -1, we get growing sequences. And when the alpha value is between 0 and 1, or between -1 and 0, then we get decaying sequences. Okay, and depending on whether they are between 0 and 1 or between -1 and 0, we'll see whether they have all on the positive side or alternating between positive and negative, as we see in these plots. Okay, so to summarize, we have seen today some examples of signals that we will be using throughout this course. Okay, the first type that we saw was the continuous time sinusoidal signal and the discrete time sinusoidal signal. And then we have seen the real exponential signals, of which we have seen the growing exponential in continuous time and the decaying exponential in the continuous time. And similarly, we have seen the discrete exponential sequence, which again, depending on the value or choice of the parameter, we can have it as a growing sequence or a decaying sequence, depending on the exponent value, not the exponent value, depending on the value alpha, which is generally represented as e power beta as well. Okay, so depending on the values of the parameters, we will have the signal coming out in a specific way. Okay, I'll stop here for today, and we will continue in the next lecture, where I will introduce you to complex exponential signals as well. So far we have seen only real sinusoids and real exponentials. In the next lecture, I will take you to complex sinusoids as well as complex exponential signals, where we will have these parameters take on complex numbers. And again, as mathematical tools that we will be using in this course, employ these complex signal types in the analysis. It is important that you have a clear understanding of these signals, because we will be using them to analyze and perform operations on several signals of interest. Okay, we'll continue in the next lecture.